On Tuesday, November 15th, I spun out and totaled my '04 Kia Optima, aka the Cricket, along with my pride. But what really happened? Park Hill South High School, 2:38 p.m. I engaged in a brutal frenzy to escape the academic side parking lot. 2:40 p.m. The on-ramp from Highway 9 to Interstate 635. Some of the intensity of the parking lot remains with me, and I attempt the on-ramp at over 50 miles per hour. The rear of the car begins to slide. I lose control, spin out, and impact the guardrail, heavily damaging my car and my bank account. But why? Why and how would the laws of physics allow such a tiring ordeal? Tiring. Tires. Whatever it is will have to do with the tires, specifically the coefficient of static friction of the tires. By pulling on an upright tire, as shown here, I could determine that the hardest I could pull the tire without it moving was 73 newtons. The mass of the tire and the weights inside was determined to be 18.29 kilograms. In this case, the tire isn't moving, so by setting the sum of forces in the x direction equal to 0, I proved that the maximum static friction equals 73 newtons. By doing the same thing in the y direction, I established that the normal force is equal to the mass of the tire times the acceleration due to gravity, or 179.24 newtons. Maximum static friction equals the coefficient of friction times normal force. Therefore, the coefficient of static friction is 0.4073. But how fast could I have gone? How fast was too fast? Well, based on the information from the manufacturer, I know the mass of the car is 1,488 kilograms, and based on measurements from Google Earth, I know the radius of the turn is approximately 75 meters and the turn is banked at an angle of 8 degrees. Since the car wasn't accelerating in the y direction, I set the sum of forces in the y direction equal to 0, and found that the y component of the normal force was 14,582.4 newtons. From there, I used the tangent function to determine that the x component of the normal force was 2,049.42 newtons, and I used the cosine function to establish the overall normal force to be 14,725.71 newtons. By multiplying this quantity times the coefficient of static friction, I determined the force of static friction to be 5,997.8 newtons, and the x component of that to be 5,939.4 newtons. The equation sum of forces along the radius equals the mass times the velocity squared all over the radius can be applied in this case since the velocity and radius are mostly constant. And substituting for all variables gives a maximum velocity of 20.07 meters per second, or about 45 miles per hour. But what does all of this mean? For one, it means I was going too fast. If you recall, I attempted the turn at over 50 miles per hour, so over 5 miles per hour too fast. But what would a crash at those speeds feel like? Based on crash test data and PlayStation 2 driving simulations, I approximated the speed of impact to be 18 miles per hour, or 8.05 meters per second, and the exit speed to be 10 miles per hour, or 4.47 meters per second, and the time of impact to be 1/4 of a second. By using the impulse momentum theorem, or force times time equals change in momentum, I was able to find that a force of 74,519.04 newtons acted on my car. Furthermore, by finding the acceleration during this time, I determined that the car experienced 5.11 Gs. However, the head and neck typically experience 2 or 3 times that amount, so 12.78 Gs in this case. 12.78 Gs is a significant amount, enough to cause whiplash and a very bad day. But consider this. When I hit the guardrail didn't just exert a force on my car. I also exerted a force on the guardrail, and by extension the entire planet. By multiplying this force times the radius of the Earth, and multiplying by time and dividing by the moment of inertia of Earth, I was able to find the amount the angular velocity of the Earth changed, because torque equals moment of inertia times angular acceleration. After substituting in all appropriate variables, then multiplying by the radius to find change in linear velocity, I was able to establish that my car crash changed the velocity of the Earth by 7.8 times 10 to the negative 21st meters per second. 7.8 times 10 to the negative 21st meters per second isn't much, but technically my actions impacted everyone else on Earth. So always just remember that all of your actions have an impact on everyone else, no matter how big or small, important or insignificant they may seem. And as always, thanks for watching.